Hello everyone, welcome back to the channel uLearn Education Online.
Today's concept we are going to see is the constant current bias method and the current mirror or current repeater circuit. So today's video we are going to see the two different circuits and why we have to use these two different circuits and what is the purpose of using it. Now we are going to see why we have to study the constant current bias method and the current repeater circuit. As we know that from the basic definition of operational amplifier means from how the operational amplifier will give better performance. That better performance will depends on the CMRR value, that is common mode rejection ratio. From the basic definition we know that the common mode rejection ratio is defined as the ratio of differential mode gain to the common mode gain. Okay, so this CMRR value will be high whenever the AC value will be less. Means if the common mode gain is less, then we can say that mathematically the CMRR value will be high. As we know from the AC analysis of the dual input balanced output differential amplifier circuit, we have derived this equation. That is, the common mode gain AC is HFE into RC by RS plus HIE plus 2RE into 1 plus HFE. Okay, now we have to decrease the AC value, nothing but the common mode gain value. Since we have to decrease this common mode gain value, first of all we have to know on which parameter the common mode gain depends. So from this equation we came to know that this RC is output collector resistance and HFE is the gain of a transistor, RS is the source resistance and HIE is the input impedance of the circuit, and here again 1 plus HFE, it is nothing but the gain. After all these parameters, this common mode gain AC is only depending on the emitter resistance RE. Okay, so this AC value will be decreased only when the denominator part will increase. So in the denominator part, only this AC value will be decreased when the RE value will increase. As we know that the increase of resistance in the internal chip based circuit may lead to some disadvantages, that is it occupies more space and also the power dissipation of the resistance will be high. But here the case is different. So in order to obtain the AC value is almost negligible to zero, ideally we have to maintain the resistance value as infinite. Means but a high value RE resistance value should be taken, but practically it is not possible. Why? Because the first parameter is increase of resistance will leads to the size of a chip increases and also the power dissipation will be high. And second parameter is the higher RE value needs more biasing voltage to set the operating points of two transistors. We know that from the DC analysis we derived how the operating point is obtained. Since in the equation itself depends on the resistance value RE. So in order to obtain the high operating point or in order to maintain the transistor to operate in active region perfectly, we need a more biasing voltage when we consider the high RE resistance value. These are the two drawbacks in order to improve the CMRR with the reduce of common mode gain. How it will overcome is, if you observe the circuit, okay, so consider the dual input balanced output circuit. So instead of taking this resistance value as very high, if you use different methods or different circuits in place of this resistance value RE, which provides the effect of increasing in resistance without disturbing the operating point of the transistor and without needing the high biasing voltages. So in order to increase the effect of resistance value and decrease the common mode gain, For the better improvement of CMRR, we are using the two methods. One is the constant current biased method and the second one is current mirror circuit or current repeater circuit. Now, we briefly going to see what are the circuits that are used in order to improve the CMRR value, and from the mathematical analysis we can prove that because of this value the effect of resistance Re will increase and the common mode gain will decrease. Now we are going to see the first method, that is constant current bias method. So in the constant current bias method, what we will see is just simply for this basic differential amplifier circuit, we will replace the resistance Re to some other circuit. Now we are going to see the first circuit, that is constant current bias method. So this is the circuit of constant current bias method. Here, in place of resistance Re, we are using one constant current bias circuit which will always provides a constant current, and also it will provide the advantage of having high input resistance. Means since the resistance value will be high, which means that the resistance Re is high and the common mode gain AC value will decrease, which will improve the common mode rejection ratio of the op amp. If a CMRR is high, then the operational amplifier will give better performance. Okay, now at the emitter terminals of transistor Q1 and Q2 of the differential amplifier, we are simply connecting this constant current bias circuit. Here, what we have to prove is mathematically, this is the current that is entering at the transistor Q3, which is nothing but the collector current IC3. This IC3 value and the current flowing through the emitter terminal of transistor Q3, IE3 should be same. So IC3 value and IE3 value should be same, and also we have to find out what is the value of IE3. How we have to maintain the value of IE3 such a way that we will obtain a constant current that is flowing through this network. So now we will see the circuit analysis. So here we are always assume that the transistor Q3 is having a high gain. So gain we are representing with the value of beta. Since the beta is very high, from the collector equation we know that for this transistor Q3 we can write the IC3 as beta times of IB3. Now what happens to the value of IB3? If you consider the IB3 is IC3 by beta, since beta value is very high, so 1 by beta will give very low value. So maximum case we can neglect the base current value IB3. So from the circuit equation of EDC network, we know that the emitter current is nothing but the summation of collector current and base current. Since the IB3 value is ignored, we can say that the IC3 value and IE3 value is always equal. Now we have to find out what is the IE3 value. Okay, so we know that what is IC3. So this IC3 is nothing but the collector currents at the transistors Q1 and Q2. Okay, now here we have to find what is the value of IE3. So in order to find the value of IE3, first we have to find what is the voltage VE. Okay, so in order to find the voltage VE, we have to find what is the base input voltage VB. So now here from this we can find out the voltage VB is nothing but the voltage drop across the resistor R1. Okay, so here the current is entering in this direction, so we can write from the Ohm's law VB as minus I1 into R1. So keep this equation as 1. Next, what is the cut-in voltage VBE? So from this cut-in voltage VBE, we can find what is the value of VE. Thereafter, we can find what is the value of IE3. So from the vector algebra, we can write the cut-in voltage VBE as VB difference VE. Okay, so from this equation, we can write VE as VB minus VBE. Keep this as equation 2. Now, we can find out the current IE3 from this circuit as, so this is the node voltage VE, let us assume, and this is minus VEE, and here it is the IE3. So IE3 is nothing but the voltage, the current flowing through the resistor R3. So we can write IE3 as VE minus of minus VEE by R3. Okay, so we can write IE3 as VE plus VEE by R3. Keep this as equation 3. Now we know what is the value of VB. What is the value of VB? It is minus I1 into R1. We have to find out what is the value of I1 from this circuit. Okay, now simply take the KVL at the input of transistor Q3. So if you take the KVL at the input of transistor Q3, so consider this path. Okay, now here we can write the KVL equation as I1 into R1 plus, now we have to know what is the current flow through the resistor R2. Since the IB3 value is 0, whatever the current that is flowing through the resistor R1, that same current will flow through the resistor R2. So we can write the voltage drop across R2 as plus I1 into R2 minus VE is equal to 0. From this we can find I1 as VE by R1 plus R2. Simply substitute this value I1 in our equation 1. So from this we can write VB as minus VE by R1 plus R2 into R1. Now simply substitute the value of VB in equation 2. Now we will get the VE as minus VE by R1 plus R2 into R1 minus VBE. Now we will find the value of VE. Now simply substitute the value of VE in the equation 3 in order to obtain the IE3 value. So IE3 we can write as minus VE into R1 minus VBE into R1 plus R2 by R1 plus R2 plus VEE by, here R3 value will be there. R3. Okay, if you simplify this equation, so IE3 will obtain this equation. Thereafter, if you simplify this, the final value of IE3 we can write as VEE into R2 by R1 plus R2 minus VBE by R3. So this is the value of IE3. So by adjusting the values of resistors R1, R2 and R3, we can get the value of IE3, which is almost equal to the value of IC3. As we know that this collector current IC3 value will always equal to the collector currents of the transistors Q1 and Q2. Now next we are going to see the second method, that is current mirror circuit or current repeater circuit. Now what is current mirror circuit? The current mirror circuit is nothing but the output current is the mirror image of input current. If you observe this circuit, simple block, here I source is the input current whereas I sink is the output current. So this output current I sink is always equal to the input current I source. Now in place of resistor RE, we are using a simple basic current mirror circuit. So this is the circuit, how it looks like. Here we are assuming that the transistors Q3 and Q4 have matched parameters. Matched parameters in the sense that they are having same gain value, same operating voltage value and same operating point. Okay, so in this current mirror circuit we have to find out whether the I1 value and IC3 value are constant or not. So from the basic assumption, that is the Q3 and Q4 have matched parameters, we can write the emitter currents of transistor Q3 and Q4 are same, the collector currents of transistors Q3 and Q4 are same, as well as the base currents of transistor Q3 and Q4 are same. Okay, so IE3 and IE4 are equal, IC3 and IC4 are equal, IB3 and IB4 are equal, and also the cut-in voltages of the transistors Q3 and Q4 are equal, implies VB3 and VB4 are equal. Now let us consider the 2 points, that is A and B. First take the KCL at the node A and next take the KCL at the node B. If you take the KCL at a node A, I1 is the entering current at node A and I2 and IC4 are the leaving currents at node A. So we can write the entering currents equal to sum of leaving currents. So I1 is equal to I2 plus IC4. Consider this as equation 1. Similarly, take the KCL at node B. Here, the entering current is the I2 and the leaving currents are IB3 and IB4. We can write I2 as IB3 plus IB4. Let us consider this as equation 2. From the matched transistors, we know that the IB3 and IB4 are equal. So, simply substitute the IB4 as IB3. So IB4 as IB3, then we can get I2 as 2IB3. Okay, so from equation, now let us consider equation 1. So from equation 1 we know that what is the value of I1? It is I2 plus IC4. Now here I2 is 2IB3 we have find. So 2IB3 plus we can write IC4 as IC3 from this equation. So finally we can write I1 as 2IB3 plus IC3. We know the relation of IC3 and IB3, which is IC3 is nothing but beta times of IB3. So from that IB3 equation we can write as IC3 by beta. So finally we will obtain I1 as IC3 into 1 plus 2 by beta. Okay. Now for the transistors Q3 and Q4, here also the gain of a transistor will be high. So beta value is high. Since beta is high, 1 by beta we can neglect. So 2 by beta we can neglect. So finally I1 value is equal to IC3. IC3 which is constant. So after proving that I1 and IC3 are equal and is a constant value, we have to find out what is the value of I1. Simply apply the KVL of a transistor Q3. So now let us consider the path as, this is the path we have to consider in order to apply KVL. So here the current is entering, so we can write it as plus and minus. So voltage drop across the resistor R1 we can write as I1 into R1 plus the cut-in voltage of transistor Q3, which is equal to VBE3 minus VEE equal to 0. Finally the value of I1 is VEE minus VBE3 by R1. VE is a constant value, that is a supply voltage, and VBE is also a constant value, nothing but the cut-in voltage of transistor Q3. And here the R1 value should be maintained in such a way that the value I1 should always equal to the IC3 value. So this is the second method that is used in order to provide the high input resistance, nothing but the high resistance value of RE, and providing a constant current. Now we are going to see the other two methods which are used in order to obtain the high CMRR value for the better performance. Now here we are going to see the third method, that is the use of active loads. Active loads in the sense use of transistors in place of resistor. So in the first two methods we are seeing that the resistance value RE should be replaced by constant current sources. So constant current sources nothing but, first one is constant current bias method and the second one is current repeater circuit or current mirror circuit. Here what we are doing is simply we are replacing their collector resistors RC with an active circuit. So this is also one current mirror circuit. So here it is active circuit which will provide the high resistance value RC. From the AC analysis we know the differential gain AD is depend on RC. Since RC is increases, AD value will also increase and therefore CMRR value will increase from the definition. So this is the use of active load. And the fourth method we are going to see is use of swamping resistors. Here, at the emitter terminals of a two transistors, the swamping resistances are used, that is Re dash. These resistors Re dash are used in order to provide the high input resistance. With the use of swamping resistors, we are having advantages and disadvantages. The advantage is the input resistance value will increase, but the disadvantage is there is a reduction in differential mode gain. Okay, we are decreasing common mode gain, but also here the differential mode gain will decrease with the use of swamping resistors, which will have impact on CMRR value, and also due to the temperature changes, the operating point of a transistors Q1 and Q2 are also changed. So the fourth method, use of swamping resistance, is not widely used in practical applications. So out of these four methods, the second method, that is current repeater circuit or current mirror circuit, is widely used in most of the practical application because of having less number of components, and also it will provide the high increase in the resistance Re, which will decrease the common mode gain and further increase the CMRR value, which will provide the better performance. And it is easy to design. Why? Because there are no resistors involved in the circuit, and it will be easily manufactured, and also it is temperature dependent. Even though the cut-in voltages will be depends on temperature, but somehow it will inherent the temperature, or we can say that it can withstand with temperature. Thank you.